Hello, everyone. Today, I would like to introduce you the integrated lithium-niobate electro-optic platform, which we believe is an emerging high-speed and power-efficient photonic integrated circuit solution for next-generation photonic needs. So my name is Mian Zhang, and I'm the co-founder and CEO of Hyperlight Corporation. Just a quick introduction of the company. So Hyperlight is founded in Cambridge, Massachusetts in early 2018, spinning out of Harvard. And we are supported in the beginning by a local VC fund. And we started to ship early prototype devices in early 2019. And then at the same time, we worked on wafer scale production of thin film lithium niobate wafers and also next generation technologies for even better performances during the last few years. And more recently, we have worked with our partners to demonstrate applications of thin film lithium niobate chips and setting a couple of records in the last few months. So what Hyperlight is offering is rapid prototype and volume production capability for thin film lithium niobate chips and technologies, and we enable our customers to get very, very high performances, and we're positioned to serve our customers globally. So the problem or the demand we're trying to target is really to solve this need of performance and cost effectiveness for next generation photonic integrated circuits. So here are a few examples of where such a combination is needed. So for example, for 5G and millimeter wave communications, especially the analog side, the extended analog frequency range can range anywhere between tens of gigahertz and up to 300 gigahertz. So there, a low voltage and high bandwidth modulator would be really, really helpful. For new applications such as quantum LiDAR, AR, VR, and also sensor applications, the demand for low loss, low static switching power, but with also extended wavelength range and sometimes gigahertz speed, this special combination can enable a lot of new applications, but these are not accessible with silicon because of the limited transparency range. And looking at the more established markets, for example, for metro and telecom and datacom, the speed of these systems are going faster and faster. And we already know the coherent system will go beyond 130 gigabaud. And then for datacom, the next generation would go to 224 gigabits per second SerDes, which would require the optics to be able to go over 100 gigabaud as well. So if we take a closer look of the for example, the established market, we see that there's this demand is not just temporary, and it will continue to increase over the next few years. And this is largely driven by applications such as in artificial intelligence, machine learning, and Internet of Things. So the most important thing, I think, going forward for example, for the data communication is really addressing the power efficiency problem, but at the same time, also being cost effective. So that's really the challenge for the next generation high-speed modules. Now, with this in mind, if we look at the available optical engine material choices today, so we can put that into this 3-axis, which I think has been used a lot of times, and I think it's a great way to visualize the way that we could increase bandwidth. So it's pretty much 3 axes to scale the data rate. The horizontal axis is the bandwidth, so basically how fast or how much symbol rate you can drive. The vertical axis is how many bits you can encode in a symbol, and then the last axis is how many channels. And then this channel can be increased in either wavelength division multiplexing through a same waveguide, or it could be a parallel waveguide, or a combination of those. So we can try to put existing solutions into the 3 axes. So if we put, let's say, bulk lithium niobate, so we see that bulk lithium niobate is actually performing quite well in terms of speed and also in terms of the encoding complexity because of the good linearity. But what is limiting for bulk lithium niobate is its scalability, and for both cost reasons and manufacturing reasons because of relatively large device footprint. So this probably explains why indium phosphide, especially in the last few years, has been really taking over bulk lithium niobate, especially in the coherent long distance market. is because indium phosphide can do as good, if not better, in both of this data rate and data modulation symbol rate and then data encoding compared to lithium niobate. At the same time, it has much better scalability due to the smaller size. Although for indium phosphide, the yield is still a challenge, and the requirements, and then most of the time it does require thermoelectric cooling, which may pose a challenge for energy efficiency or cost for future systems. But nevertheless, it's still much better than bulk lithium niobate. So because perhaps of the shortage of this tool platform, this is where silicon solutions really comes in. So if we look at the silicon, the part that silicon excels at is this multiple channel or wide parallel approach, where you can put more wavelengths or more channels just by simply integrating more component. But what silicon is suffering is the device performance. So if we compare the silicon with, for example, indium phosphide or bulk lithium niobate, it's actually the speed that you can drive, at least in the published domain, is much lower than what has been achieved on indium phosphide and bulk lithium niobate, even after decades of development. And then the encoding also it suffers compared with this two because of the less linearity and the more absorption loss. So considering this, the solution here is present a non-ideal combination, of course, which one to use, whether it's wide parallel or single with high speed. This is still a complicated discussion, and it's dependent on a lot of factors that's beyond just the transmitter devices. But I think the more, if you look at the history, it's normally a combination of the three axes with the least amount of effort. So for example, to reach a certain speed, you probably want a good combination of high enough symbol rate with the reasonable channel number plus a reasonable encoding level to really get to a decent speed. So so now from the photonics integrated platform, I think the more degree of freedom that you would be able to provide here, the better. So if we put thin film lithium niobate here, we can clearly visualize the advantage. So in terms of driving speed, so we know this is a huge improvement even from the bulk lithium niobate. And this is clear from the literature with just a couple of years of development. And it's people already show that over 200 gigabaud can be done on thin film lithium niobate with very high level of encodings. And at the same time, I think this access is probably most debatable. I think our intention here is not to say this is going to be better than silicon, but at least I think it's comparable in a sense that, for example, if you try to make beyond 200 gigabaud transmitters on silicon, it's much more challenging compared with that doing on thin film lithium niobate. So in that sense, the scalability at those kind of speed for lithium niobate could be comparable or even better for these very high performance devices. So if you consider all of this aspects, thin film lithium niobate really has a multiplicative advantage when considering the all possible axes of scalability for future devices. So a little bit into the details. Again, this is different way to visualize this. Really, the silicon transmitters are suffering in voltage and bandwidth, but really gains in scalability and thermal resistance and doesn't require thermoelectric cooling. Indium phosphide has much better voltage and bandwidth performance, but has and also smaller size actually, but it's not as scalable as silicon. And for bulk lithium niobate, this is sort of the existing incumbent technology. The voltage is also high. The thermal resistance are excellent, but it's lacking scalability. So if we look at the thin film lithium niobate, we know that we can achieve a low voltage, we can achieve high bandwidth. The insertion loss can be really low because of the intrinsic material property and also the smaller size. But and also the size, just to give an idea, it's actually pretty comparable to silicon in terms of EO modulation efficiency. And then the scalability, which accounts for how easy this device can be made at scale, based on our investigation, is also excellent. So, so what we want to show in this chart is that thin film lithium niobate is really a strong contender for next generation optical engines. So what is the difference of the lithium niobate or the thin film that we're talking about with the existing lithium niobate approach? So just to keep the discussion at high level, existing lithium-niobate employs the bulk substrate and with weakly confined optical mode in this waveguide defined by either proton diffusion or titanium ion diffusion. We're defined as weakly waveguide, weakly guided optical mode with electrodes that are typically separated by tens of microns. So this results in weak modulation efficiency and very long devices. And an approach thin film lithium-niobate takes is very similar to silicon on insulator platform. It just instead of silicon on top, you replace that with lithium-niobate waveguide. And these waveguides are typically on the order of a micron or less. So it's a very close size to silicon. And the refractive index is about 2.2, which is very close to another popular platform, silicon nitride. So with this new platform or with this new approach of doing the thin film, this is roughly, I think it's roughly scaled to length, not to thickness. You can see that the thin film lithium-niobate modulator is dramatically shorter than a bulk lithium-niobate, but at the same time, this actually achieves much lower voltage, as we demonstrated early on in 2018, that you can reach into the 1 volt range with over 40, 50 gigahertz bandwidth using a thin film approach. And remember, this is only the first generation devices. That's not a few years after the thin film platform was introduced. So right now at Hyperlight, so this is after we did the internal development, is that the second generation, we call the second generation, the CMOS voltage millimeter wave bandwidth electro-optic PICS can achieve some really, really amazing numbers. So I think the most relevant wavelengths here is probably 1310 nanometers and 1550 nanometers. And we also give, I guess, just a broad reference that we find in the literatures out there that describing silicon modulators. So the 1310, I think, has a natural advantage that it's a shorter wavelength, so less phase shift is needed. So therefore, the voltage there is a little bit lower. But you can see that these are significantly lower voltages than silicon. And also, this is the V-pi. This is actually the full swing. You need to turn it from on or off. So in reality, depending on what is IMDD or coherent modulations, you actually only need a fraction of this voltage. So the V-pi of the thin film lithium-niobate really puts this into the realm where this could be directly driven by CMOS circuitry. And then the amazing thing is at the same time, so this is simultaneously, it is possible to achieve a 3 dB bandwidth over 100 gigahertz with this kind of voltages. Now, if you compare that with silicon, you're looking at a 4 to 6 volt at probably low R frequency. And when you go to 40 gigahertz or 60 gigahertz in future system, your bandwidth there is your absolute voltage there is going to be much higher. And then what's even more exciting is that the 6 dB bandwidth, or if you try to see the usable range of the thin film lithium-niobate, it's actually beyond 300 gigahertz. And some of our customers has really indeed took this to those frequency ranges. So it shows the compatibility for future system if there was ever a need to go to those frequencies. And when you compare the V-pi-L, and now we're just comparing with the silicon reverse bias Mach-Zehnder broadband Mach-Zehnder, the lithium-niobate is actually a little bit better. But it's very comparable size to silicon. So the size is of lithium-niobate is big. It's also a mystery. Another really key important here is modulator loss. So because of the intrinsic low insertion loss or low absorption loss of the material, it's possible to get less than 1 dB for the entire chip system, even with many centimeters of waveguide wrapped around. And this is in stark contrast with silicon, which for that modulator is typically over 6 dB. And this is also another great factor for reducing the optical power or the power consumption furthermore. And at the same time, thin film lithium-niobate, they maintain the regular impedance voltage. There's something special there. And then the optical efficiency is also quite good. And of course, to make a great photonic platform, you need additional components other than just the EO modulators. So this is very fortunate because the index is, like I mentioned, is around 2.2. So there's a lot of research in silicon or in silicon nitride that this can be easily leveraged to develop. So we very quickly iterated and developed a vast library of passive component, also including a slow active such as heaters that to complement the functionality of this platform. So with that sort of in mind, so we made these prototype packaged devices. And we work with Nokia Bell Labs as collaborations. we show that this is actually using the Gen 1 device, not even the Gen 2. And we can do a record transmission of 700 gigabits per second over 10-kilometer optical fibers using a single modulator. So this is 7 times faster than the line rate with transceivers today. But of course, this is a theoretic experiment, but it still nevertheless shows that there's a lot of room for future higher speed line rate optical solutions. This can also be used for coherent, just like its predecessor, bulk lithium-niobate, because of the excellent linearity. And now the particular voltage is going to help a lot at when the analog bandwidth goes higher. So here in this case, we went all the way up to 100 gigahertz with 200 gigabaud transmission for coherent with the net data rate of 1.58 terabits per second. So I think perhaps beyond just modulators, there are, if we look a little bit into the future, it's not just about it's about better modulators. So there's a lot of subsystems that can be enabled when you have a very low loss system and a very high modulation efficiency system. So for example, some of these devices are just not possible in current platforms. For example, frequency shifters, which we have demonstrated, it is possible actually to shift, say, 50% of the power of one laser to a particular frequency offset with a dedicated amount of power. And it's also possible to do a broadband comb generator by cascading different modulators on the same chip. And you can get, say, 10 copies of, or designated copies of a single tone laser oscillator with very high efficiency, 40–50% overall conversion efficiency into a multi-tone oscillator with minimal RF power. So this is a great way, I think, for the future system, where I think a lot of companies and research institutes are exploring the multi-wavelength oscillator technologies, and that can what's sort of it's more interesting here, and maybe even from a practical sense, is that this comb generator can integrate together low loss within low insertion loss with other modulators, and thereby give you the system level advantage. So these are some of the things that are possible for some of the future applications. So I think it's hopefully I've convinced you that there is enough motivations to explore, at least explore this material for commercial applications. But the perhaps a very important topic that I want to bring up is the scalability, because this addresses the other side, right? We show like there's a potential to reduce a large amount of power consumption, but what about the cost? So that's the other side of the equation. So of course this is still in an early stage, so it's not as developed as for example silicon or indium phosphide, but there are some fundamental fundamental or first principle data point that we could try to derive what would the cost look like when these are shipped at volume. So a lithium-niobate crystal, they're made the same way as silicon. So they're pulled from a molten salt of crystals. So this is fundamentally a high yield and low cost process. And then the way the thin film wafers are made are also very similar to silicon on insulator. It's through a smart card process. So this process is now actually quite established. And then this process is also fundamentally not of high cost. And then at Hyperlight, we want to show that this is not just work on single devices. So we made this on wafer scale using deep UV lithographies. And then for these ones, just to compare the best achievable loss, we can get to less than 0.1 dB per centimeter for both passive and active devices using DUV lithography, and then maintain a pretty good edge depth variation as well. Just even on a without optimized without too much optimization. So this just shows like it's fundamentally the wafers, they can be low cost, and then these chips can be made at scale. So just another comparison of what we mean by here. So this is not a 200 millimeter or 300 millimeter process like silicon. I think for lithium-niobate, the more common size is 6 inches. But there are roadmaps toward 8 inch as well. So here it shows a DUV demo wafer that we did internally on a 6-inch wafer, and comparing that with the existing bulk lithium-niobate modulator. So you can see that this chip that's shown here, the VPI of this is about 2 to 3 volt, and then the bandwidth is over 100 gigahertz. So this chip with similar or better performance, it's a lot smaller than this, and it probably can bypass this this power-hungry amplifier as well. But again, we understand this technology has been there for quite a while, but this is a good reference to show that even with a 6-inch wafer, you can produce a significant amount of chips that would be interesting to the market, and then potentially achieve a low cost. So with all these points of discussion, so I think the part that we wanted to communicate with the community is our opinion for the commercial deployment or the challenges for lithium-niobate photonic integrated circuit. So hopefully we have give some evidence for the benefit and also the readiness of this platform. So lithium-niobate, it really offers a very good performance today, with a lot of room to improve for future demand, especially in terms of optical transmitter functionalities. We show that through the sort of a fundamental first principle approach that the cost, it can be cost effective when it ships at volume. And then there's also evidences that because of the high performance, you can enable some new architectures that are not previously possible. And then finally, there is a path for potential drop-in solutions to have, with the drop-in solution, but still have a system level power improvement for present technology challenges. So this is something that can be adapted on a relatively short time scale. So of course, as a new platform, there are challenges to be solved. So first one is customer adoption and validation does take time. So this is something Hyperlight and with its partners are working very hard on. The second question is really integration strategy with additional components, and this needs to be validated as well. For example, photo detectors. So this in a part, I think it's worth a lot of discussion. Is what level of integration, and it's probably need to be put into context for different applications, and it need to be evaluated on a system level. For example, it may be more difficult to separate this with detectors, but because it can save driver complexities, that could be an additional advantage. But of course, that need to be evaluated all together. And also the resilient and the mature supply chain needs to be established. And then this is again a community effort, and then it may take a little bit of time. So from Hyperlight's perspective, Hyperlight really believes in, because of our experience with this material, we really believe this material is providing at least a complementary functionalities for what photonic integrated circuits could offer today. So I guess in the interest of accelerating this platform, what Hyperlight is offering is that we offer custom devices that we could tape out, actually real devices in relatively short turnaround time, around 8 weeks. We can customize modulators, customize photonic integrated circuits with different functionalities based on our customers' needs. And at the same time, we also open to work with customers on standardized, low-cost, high-volume devices, which may take many months or even in order of years to develop a specification and then a particular customization for certain applications. So these are the particular effort that Hyperlight is hoping to be able to contribute to the community. So that is the end of the talk. So if you're interested for samples or collaborations or learn more about our products, please email us at the email address below, info@hyperlightcorp.com. You can also reach out to me personally at Mian, M-I-A-N, at hyperlightcorp.com. And also the image shown here is something that we are interested to explore with the community as well. It's basically a packaged version of the thin film lithium-niobate, and you can get a sense of really the size reduction and how does that compare with the traditional lithium-niobate in size, and at the same time this module would run at a single volt, but with over 65 gigahertz bandwidth. So that is for my talk, and hopefully we can spend some time on Q&As. Thank you.